So it is my great privilege to introduce our distinguished speaker of today's first talk, Professor Louis. Louis Marmet is an adjunct professor of physics at York University in Toronto. He studies light matter interactions and their importance in our interpretation of astrophysical phenomena. Marmet has obtained his PhD in physics from the University of Toronto with specialization in experimental quantum optics. As an Alexander von Humboldt Fellow at the Ludwig Maximilian University of Munich, he conducted research on quantum chaos in atomic systems. His career at the National Research Council Canada focused on high precision atomic clocks and laser cooling of atoms to microkelvin temperatures. Marmet is currently collaborating with a group of York University on the experiment that uses an atom interferometer sensitive even to detect laser heating from a single photon interaction. Professor Marmet's passion for physics appeared at an early stage, inspired by his father, who was also a physicist and introduced him to the principles of measurement, inquiry, and profound desire to understand the world. His interests led him to a broad range of activities that include amateur astronomy, photography, mathematical modeling, philosophy of science, and astrophysics. These diverse skills are key for perceiving nature with a distinct clarity as he recognizes that illusions pose a constant challenge to knowledge. This unique lens is especially important in cosmology, a discipline at the intersection of science and philosophy. Marmet believes his perspectives can offer a fresh understanding of the universe we inhabit. Since 2018, he has been facilitating a discussion group focused on cosmology, fostering dialogue and explorations of these themes. So I request Professor Louis to take over the session with this brief intro. Sir, please hand over the session and deliver your talk.
Thank you very much, Sravan. Let me share my screen here. Yes, thank you very much. I wish to thank the Bhaktivedanta Institute for inviting me to speak today. As you saw, my background is in experimental quantum optics, and so my view of the universe is very based on what we see. And I'll start this talk with a well-known parable of the four blind men and the elephant. Here on this slide, we see four astronomers who are trying to measure the Hubble constant, the constant that gives us an idea of how fast the universe is expanding. And there are many techniques that are used to determine this constant. And unfortunately, when you get the values with these different techniques, the numbers disagree. And the difference is quite large between the smallest and the largest. And as you've seen in previous talk already, this is called the Hubble tension, and it's a fairly serious problem in cosmology because the expansion of the universe is fundamental to our cosmology today, Big Bang cosmology. And so I think here that we have a case that is very similar to the parable of the blind men, is that there's something we don't see, and that's why we don't get the same numbers for these different techniques. Outside, of course, of experimental difficulties, these are very difficult measurements. So throughout this talk, my claim will be that without optics theory, our interpretations of what we see are rather blind. There are many questions to discuss in cosmology. Of course, too much to talk about in a 45-minute talk. Here, I'll limit this discussion to a very few simple questions concerning the approach we have to cosmology and the scientific method in cosmology, and finally, the interpretation of observations, which are not unique. There may be many ways to interpret what we see. So to simplify things, I use two categories. First of all, there's an empirical approach to science, which is to observations or knowledge, which is usually done through the scientific method. And there's the interpretive method, which is more from personal experiences and observations and spiritual beliefs. So we can separate different cosmologies that exist with these criteria. And then on this axis here, I split the different cosmologies depending on whether they claim the space is expanding or non-expansion of space. So in this talk here, I will mainly focus on the empirical cosmologies, and I'll take lambda CDM, the most recent version of the Big Bang Theory, as an example. And on the non-expansion side, I'll discuss the static plasma cosmology. Tim Eastman discussed this a bit yesterday, so this will be a continuation of that discussion. Now, the scientific method in cosmology is a little bit hard to apply because some of the ideal assumptions made for this by the scientific method cannot be applied. So, for example, when our theories are supposed to be testable, but it's very difficult or impossible to get feedback from what we do. We can do experiments, but we don't have experiments where we can, for example, spin a galaxy in the other direction and see what happens. Also, when we see strange phenomena, it's very difficult to get independent confirmation of what we see because we don't have access to all the stars and the galaxies to change the initial conditions. And so while most of the cosmology uses the scientific method, some parts of it are rather difficult or impossible to do. George Ellis also discussed this yesterday in great length. So I'm going to move over to our observations. Now, our observations with the fancy telescopes we have are an extension of our senses. And we understand this part, I think, very well. I was discussing with a philosopher some years ago. He was telling me, well, the James Webb telescope is a new instrument. How do you know it works? And I showed him this figure here. I said, well, this telescope is actually a Cassegrain telescope, which was invented 350 years ago, and we understand it very well. And actually, I find it amazing that the diagram put up by NASA is very similar to the diagram that Cassegrain had in his book in 1672. So as far as I'm concerned, like for an experimental physicist, our observations, our instruments are just an extension of our senses, and this is very well understood. Where it gets more difficult is when we look at things that are extremely far away. So this is the galaxy here, MOM Z14, which is the farthest confirmed galaxy we have so far. This is so far away that there could be optical illusions on the light that's reaching us, and an objective interpretation of what we see becomes much more difficult. So let's start with the measurement of the Hubble constant. Almost 100 years ago now, Hubble started looking at photographic plates and analyzed galaxies we were seeing. And so what we know for sure with our instruments are the light we're getting from it, and we can analyze its spectrum, for example, its intensity. We know the angular size of the objects we see. We can see galaxies somewhat larger, appear larger on the photographic plate. And for objects that are transients, so we can measure the time duration of these objects, like supernovae, pulsars, all these things. These things are measured, and we understand very well what we see. When it comes to interpretations, though, this becomes more difficult because then we have a choice of understanding what we see. And for example, a redshift, there are a few different ways to interpret what the redshift means. In Hubble's time astronomy, the interpretation was that redshift was caused by a velocity, a Doppler effect that reflects a velocity. And for example, the luminous flux, also how bright the object is, we see that as meaning distance. So the fainter the object is, the farther away it is from us, which is our common experience. So Hubble plotted this relationship that he saw with many galaxies, and he saw that when the object is further distant away, the redshift becomes larger, which was a very important discovery, actually. And they tried to explain it by interpreting what redshift means and what distance means. And at the time, of course, Einstein had just come up with his general relativity theory. And so this was immediately applied to try to understand what Hubble had seen. And so the interpretation is that space expands, and the expansion increases distance to those galaxies we're looking at with time, and therefore this is a velocity that produces a Doppler effect and dimming of the galaxies. They're getting fainter and fainter because of the velocity, the recession velocity of these galaxies. And since then, there's been many observations to try to see if this made sense. I'm going to just give you one example of observational evidence. I think this is a very good, maybe the best result we have. So this plot here shows the luminosity distance, that is the distance we get from the luminosity of an object as a function of redshift. And so the bigger the redshift, the distance increases. This is a measurement of supernova distance. And as you can see, this is a theoretical equation from a solution of Einstein's equation. And by adjusting various parameters, so there's the Hubble constant here again, but also the amount of matter, the density of matter in the universe, its curvature, and of course, the dark energy lambda constant. We can fit these data extremely well, as shown by the black line here. This is one of the many observational evidence that we have that our description of the universe is correct. Now, there are many more, but I think the previous speakers and the speakers tomorrow also later will discuss all this. So I'll just list the strength of the expansionary cosmology. And of course, those that are important are that we have an agreement with the redshift distance relation. So that's the curve I just showed. It describes the cosmic microwave background very well. It explains the nucleosynthesis of light elements in the cosmos, and the evolution of structure, galaxies, filaments, and so on, is also modeled fairly well. Of course, there's consistency with general relativity since it's derived from relativity, and it's the best model we have so far. Now, on the other hand, there are weaknesses as well. since the interpretation implies a Big Bang, there is a period of very dense energy at the beginning of the universe. And at these high energies, the cosmic laws are not known very well or not at all. And another problem is that there are many coincidences that appear. We need fine-tuning, and some ad hoc assumptions must be made to make all this work. And with time, like since the history in the last century, essentially, there has always been issues showing up and tensions, and the cosmology we had has always been subject to revisions. Now, for some people, this is just an indication of how science progresses, but this is different actually from, for example, if you take quantum mechanics, which also is about 100 years old, the equation written down by Schrödinger hasn't changed since then, while in cosmology, the equation describing the expansion of the universe, for example, has changed drastically. So it seems the model is still, after 100 years, a bit on shaky grounds. So I'll break my talk in two, showing this photo here, just to show that, to explain what I see when I look at this. Of course, we see all these clumps of light, which we know are galaxies, and they're formed by gravity. Gravity pulls matter and creates all these nice structures. But in addition to this, what I see in there is that this light we see is emitted by hot plasmas. They're the stars that give the light off. And the third thing I see as a specialist in optics is that, well, we see light. And so this light has traveled extremely long distances to reach us, and might have been affected by this long journey toward our telescopes. So when you think about cosmology, of course, gravity is very important. But as Tim Eastman said yesterday, plasmas have a very important role because they're not fully shielded, they're not neutral. And I wrote here some example of the Boltzmann transport equation and Maxwell equation. And I describe this interaction here of the plasma with currents and so on as fields tells us tells chargers how to move, and chargers tell fields how to curl. Sort of to repeat John Wheeler when he was talking about gravity. Now, my specialty is quantum optics, and of course, the important equation here, Schrödinger's equation in quantum electrodynamics, describes how light carries energy and momentum between these charges of the plasma. And this is also a very strong interaction at the scale of the universe, comparable to what plasmas and gravity are doing. And in some cases, actually, it is stronger. So let's go back to Hubble. And when he's not with Einstein looking through the telescope, he also had some doubts about the interpretation of redshift, or he knew that there was another possibility. So in 1932, Macmillan wrote that the interpretation in terms of light quanta, quantum mechanics, is much less disturbing. And even Hubble was trying to find a way to explain the redshift in a way that does not involve actual motion. That is, no expansion. The effect is on the light that's coming to us, that's being reddened. So Fritz Zwicky, everybody knows him for his hypothesis of dark matter, also suggested that photons lose energy as they travel. he didn't know exactly how, but of course, some properties were very important to explain what we see. Most critically, the effect had to be wavelength independent. There had to be no diffusion of light, of course, otherwise we wouldn't see all these galaxies at large distances. There had to be no absorption of light, and the process would follow essentially a reduction of energy or intensity that would be proportional to some cross-section and the number of interactions on the path to between the galaxy and us. So the interpretation suggested by Zwicky was that a spectral interaction produces a redshift as light propagates through the intergalactic medium. Now the question is, how does that happen? How can we explain this theoretically? And I don't want to you to read all these papers here, but many people had many ideas and published all these ideas since 1931. So this is a sample of publications in the last 100 years. And if you look at these papers, about 33% of them assume a redshift mechanism. They don't know what it is, but derive their implication in terms of cosmology. Another 33% propose some new cosmic physics to fit observations, but unfortunately, this doesn't turn out as being measured or observed on Earth in the laboratory, and so the theory never gets accepted. And finally, there are many people who publish papers that use established physics, but they ignore some mistakes that are made, and their predictions are not very useful. So given the large number of papers, and this was kind of lumped into one category called tired light. This is a name actually proposed by Zwicky, but it didn't take long for other scientists to refute these theories. Ned Wright actually refuted most of these theories, and there were even experimental tests done to try to see if we could see redshift in electrons caused by electrons, and but there was a null result obtained in 1936. Actually, it was fairly early. So, as this webpage says, there's a blurring of distant objects. That is, if you have a blue photon coming in that goes through a medium, and you assume energy conservation, momentum conservation, causality, it is impossible to produce a red photon, a redshifted photon from it that travels in the same direction. And this was argued actually fairly early too, in 1953, by Atkinson, who discussed this in more detail. So it would seem that since there's no physical mechanism that can produce this, finding a tired light theory that would explain the cosmological redshift is a lost cause. And this is impossible as it is now. And this is the common consensus in astrophysics today. Now, all hope is not lost. Quantum optics has, there's been a lot of developments in optics science since Atkinson's argument in 1953. And one effect that is very interesting, that was actually predicted in 1933, is the Kapitsa-Dirac effect. And it was predicted that electrons should also be diffracted by standing light wave. And this is a very small effect. It was only actually experimentally measured in 2001, almost 70 years after its prediction. But Kapitsa and Dirac were right. Light can interact with electrons. and produce an exchange of momentum between the light and the electrons. So I'm going to spend a bit more time here on this slide just to show how the effect works. Essentially, to get the standing wave, we need two beams. One photon, a blue photon coming in, and one red photon coming in. And they interact with an electron at rest. During this interference, because they interfere, they give the electron a momentum kick, which pushes the electron up on this diagram. And the photon is scattered into the initial red beam by a stimulated emission process. So that's again Einstein coming here to help us understand what's going on. Because if it's a stimulated emission process, that means the red photon is going exactly in the same direction as the initial red photon. And so here you see that we have initially a blue photon and a red photon. And at the exit of this experiment, we have two red photons and an electron with a little bit of momentum that's recoiling. Now, if we put this in the context of a bit more realistic spectrum of light, we see that we can have light with a spectrum that has two blue photons and one red photon interacting with another beam that is also bluer, two blue photons, one red photon. Then once you go through interactions with a few electrons, what you get in the end result is that the spectrum of this beam has been shifted to the red. Now there are two red photons. Same for this beam here. Now the properties of this are very good in the sense that it's a Doppler recoil redshift. The electron recoils and emits the red photons. So it has the properties that the redshift is wavelength independent. And because it is a recoil, it is really a velocity of the electrons that will stretch time-dependent light pulses or any pulse emitted by a transient. So the second property is stimulated emission, because it is this effect that's implied in the electron-induced redshift. The beams don't change direction. That is, the initial beam coming in this way exits here in the same direction. Stimulated emission is well known for its operation in lasers, where you have very collimated beams. And that's because there's no scattering that changes the direction. There's no diffusion of the direction of the beams. Because the process is an interference effect, it's linear in intensity, and this becomes important for the low intensities of intergalactic space, where light is not very bright. There's some momentum diffusion. That is, after the process, the electrons are heated. They have acquired momentum and therefore have a higher temperature. And of course, the process is proportional to the electron density. The more electron density you have, the higher, the more often the process happens. And so this is described as a cross-section, sigma, and the average number of electrons involved in the interaction. So the Kapitsa-Dirac effect is actually an effect that makes this type of redshift possible. You have beams entering a black box, beam exiting a black box with a redshift on the spectrum. So let's look now at observational evidence for this. Since there were papers published from early on that assumed that if there is such a tired light redshift, they derived a cosmology. In the 1930s, Nernst and Macmillan derived what's called a Nernst-Macmillan cosmology, where they showed what the equations would be for different distance measures. And so, according to this is simply a solution, actually, of the Beer-Lambert equation. The distance depends on the logarithmic function of 1 plus z redshift. And in a recent paper, 2022, this graph was published, which shows all the black dots here are diameters measured for different galaxies. And even the red dots here show diameters of galaxies measured by the Webb Space Telescope. And you see that this follows the line predicted almost 100 years ago as the angular distance measurement. Now, you'll notice that the lambda CDM prediction would imply that the diameter, the apparent diameter, would actually increase at very large redshift, and it disagrees with observations. So what's happening here? And to explain that, the standard cosmology says, well, our galaxies don't have a constant size. They're not all 10 kiloparsec in size. There's evolution of their diameter because we're getting near the Big Bang here at these distances. And so galaxies were not this diameter, but much smaller just after the Big Bang. And that's why we see them below the predicted line of lambda CDM. Here, the static cosmology does not have that option. Galaxies, there's no evolution of galaxy, pardon me, in static cosmology because essentially there's no Big Bang to trigger all these galaxies to start forming at the same time. And so while each galaxy evolves on its own, there's no common starting point that has triggered and synchronized all this evolution. And so with this very simple equation, we fit data very well. Number two, there was this test that was derived or invented in 1930 by Richard Tolman. And he said, well, what we could do is measure the surface brightness, excuse me, of galaxies to see if the universe is really expanding or not. And in his paper, he concludes that if the Tolman signal is 1, then that shows there's no expansion. If the Tolman signal is 4, then that shows there is expansion. Now, these are actual fairly recent results. And what is seen is that there is actually no change of the signal as a function of redshift. And so the surface brightness is constant, which means a Tolman signal of 1, which shows there's non-expansion. Again, this is given by a very simple formula and show on this graph what would be expected if the universe was expanding. And it's, of course, very different. But again, lambda CDM claims that galaxies are evolving, and therefore they are actually brighter. Brighter galaxies is down on this graph. They are actually brighter than expected. But this is still not very well understood. As they say here, a large portion is left unexplained of this evolution. This is the same graph I showed earlier with the supernova distance as a function of redshift. In this case, the static universe, the static cosmology equation agrees. It's again the same equation, just a factor here, 1 plus z, because of the stretching of the light curve and, of course, the redshift. And so here the agreement is extremely good. It actually covers the black line that's underneath here. And so this constitutes observational evidence number 3 for the luminosity distance. All that is done with this very simple equation that essentially has only one parameter, the electron density in space on the path between the galaxy, the supernova, and us. Now, it would be interesting if we could actually independently measure this number density, because, I mean, while this effect might exist, if its amplitude, like if it's very small, then it would not explain the cosmological redshift as an electron redshift. And we've been lucky in the last 20 years. There's been a discovery of fast radio bursts. So for those of you who don't know what it is we've detected some very short radio pulses with radio telescopes that come from very distant explosions. The model is not quite understood yet, that happen in very distant galaxies. And starting in 2017, these explosions were located very precisely and associated with a host galaxy. So while we could measure the fast radio burst with our telescopes, and the dispersion of the radio waves, which is proportional actually to the number of electrons, we could also measure its redshift because we could take the spectrum of the galaxy. So two processes now are happening in parallel. There's this radio pulse traveling through intergalactic space, and from plasma physics, we know that the pulse is dispersed, and it's calculated easily with this equation here that is, it's essentially proportional to the number of electrons that are interacting with the pulse. Now, the electron redshift for the static cosmology depends exactly on the same quantity, the number of electrons that have interacted. And therefore, because these two quantities are the same, we can just simply take the dispersion measure and plug it in this equation, and we get this very simple relationship between dispersion measured, that's measured with radio telescope, and the redshift, with this proportionally constant here, which is the redshift cross-section, again, given by theory as being this value. So by 2025, last year, there were over 120 fast radio bursts that were localized. So we have, for each radio burst, here we have their redshift, and then we have the dispersion measure, and there's a host contribution, that is a host galaxy also causes a little bit of dispersion, which is added on top. But this means that we should expect all measurements to be above this line here, and essentially no measurements below, because that's what's contributed by the intergalactic medium. And so the equation, the simple equation that I showed on a previous slide is plotted here. That's this line. And the fit is, the match is very good. There's no adjustable parameter. I just use a calculated cross-section. And it confirms that this value is correct to about 5% uncertainty. So this observational evidence has very profound implications, because this means that the electron redshift is strong enough to contribute to account for 100% of the cosmological redshift. And therefore, if this is what's happening, what's redshifting the galaxies, the light of the galaxies, then there's no room left for space expansion. I showed you earlier how the process gives a momentum kick to the electrons and therefore heats them, increases their temperature. And there's been a problem in solar physics that is still unsolved. And the question is, why is the solar corona this hot? Now, solar physicists have calculated different effects. There are magnetic lines crossing and all sorts of alpha waves propagating through the solar corona that gives them some heat. But when they add all these effects, it still does not give enough energy to bring the solar corona to a 3 megakelvin temperature. But if you include also the light interacting with the electrons of the solar corona, then you can see that it brings the temperature to 3 million Kelvin. The same thing is visible here in galaxy clusters, where they've looked at the energy in the plasma that's in the middle of all these galaxies. And they find that the thermal energy in the core is about 10 times more than gravity alone should produce. So gravity does produce heating of this plasma. And my claim here, of course, is that it's, again, the redshift process, the electron-photon interaction, that provides the rest of the energy to bring these the plasma in the galactic clusters to such a high temperature. So now here I'm getting into a bit more ahead of myself, in the sense that the theory to understand this is not derived yet. This is future work. But I've plotted on this graph here, which shows the temperature of the plasma as a function of the density. I took the original image and added the intra-cluster medium. That's the previous slide. That's what I show on a previous slide. And there's another plasma that's has even a lower density, and it's the intergalactic medium. And it should be at a very high temperature, essentially because there are no collisions to dissipate the heat. And I show this here as this familiar diagram, which represents the microwave background, but at a temperature of 6 billion Kelvin. Now, the reason we don't see it at 6 billion Kelvin, we only see it at 2.7 Kelvin, is that electrons have an extremely low emissivity. The interaction is very rare between a photon and an electron. And this is what I write here. Compton scattering happens only, the mean free path is about 40 trillion light years. So it's a very small emissivity. And so while the plasma itself is very hot, the radiation associated with it is very cold. It would be down here on this graph. So this is research in progress, but the plasma is cooled by pair production. It's heated by redshift interactions, of course, cooled by pair productions, nuclear reactions. There's a cycle between the redshift of the microwave background and the blue shift caused by heating from Compton scattering. That's called the Sunyaev-Zeldovich effect. And to achieve the black body spectrum, there needs to be multiple Compton scatterings. What's important here is that this means that the universe must be much older than 40 trillion years so that we can achieve this black body radiation spectrum. And then in a universe that's that old, this gives a lot of time for elements to form. And not only the light elements are formed, well, the light elements are formed in the stars, and with that amount of time, they can reach the proportions that we measure today. An interesting thing is that this becomes comparable to the 311 trillion years that I read, which is calculated age of Brahma. So for some reason, this number here is now very much in agreement with what we get from just calculating Compton scattering events in the low density medium. One last thing is experimental evidence. I like this picture because this is a paper on free electron lasers where they use a blue laser, they describe it as blue laser, but at the exit here comes out some coherent emission, which is redshifted. And of course, they benefit from the large density of electrons in the free electron laser. Now, there's a caveat to this, is that this is not exactly the same process as what's happening in space. They essentially had to use nonlinear effects to be able to see the signal, but it shows that it's possible to get a redshift in electrons from an initial light, and it's coherent. That is, it's propagating exactly in the same direction. I won't have time to go over this. There's an experiment that I plan to use at York University to try to measure some aspect of the redshift in electrons. Here, though, it's going to be done with atoms. And so I'll finish by discussing the static cosmology, its strength. It's based on known physics. It can be understood with the physics we've already discovered in the lab. It has the same evidence observations, that is, the redshift distance relations. The cosmic microwave background can be understood, as I've discussed, like elements and evolution structure. I didn't have time to discuss this consistency with relativity. This interaction with the electrons produces a pressure, which would be described as a lambda term in the equation. But it's made predictions too. It's not only that we fit the distance, it's actually this was predicted almost 100 years ago based on the redshift distance equation. It predicted that a heating of solar corona and interstellar plasma, the cross-section, the calculated cross-section is confirmed experimentally. And actually, what I'm working on now is a relationship between the Hubble constant and the temperature of the CMB. And I won't disclose what number I'm getting, but it's very close to one of the 4 measurements I showed earlier. All this without antimatter, without coincidences, just straight quantum optics. Weaknesses, they're not at the physics level, they're more at the procedure level. We need to have general relativity, plasma physics, and quantum optics all at once. Interdisciplinary knowledge is essential. The infrastructure is still in development, and so some hypotheses must be accepted temporarily until we have a better description. Quantum optics and plasma physics are frameworks. They don't tell us what the cosmology is, so this is still in development. And of course, there are some questions that are asked all the time that are not, that are the limit of science. And so there are things we cannot know with science. And I think these boundaries have to be acknowledged with humility. So I'm going to quote here Max Planck's. I'm sure you've all read this. I'm not trying to convince people that this effect is real. I'm just trying to expose the new generation to this possibility so that you're familiar with it And when you read papers, you think, this could also be a tired light effect in electrons. And hopefully by becoming more familiar with it, there'll be more people working in this field and to study its possibilities. So I'm going to leave you with this. Thank you very much.
Yeah, thank you, Professor, for your brilliant and truly inspiring lecture. I would like to express my sincere gratitude for sharing such profound insights. I hope this talk has enriched the knowledge of many of the participants, especially the serious researchers into fundamental cosmology and also quantum optics. So we understand that there is so much to explore at fundamental and foundational level. It has opened doors to budding researchers to explore more. Thank you once again, sir, for such a remarkable lecture. I hope this talk has lit up many young minds with interesting questions as well. So if time permits, we will try to take 3 or 4 questions. First question, please. This question is by Dr. Bharat Pandey from Government PG College, Ranikhet from India. He is asking, sir, is it possible that what we perceive as the structure and evolution of the universe is not an absolute reality, but an optical illusion emerging from the assumptions embedded in our cosmological models?
Yes, thank you for the question. I think it is. I think, I mean, this is a question that's beyond science, really. What the actual universe, like the absolute reality is, I think we don't know. And I'm not sure the scientific method can actually let us know what this reality is. All we do is to observe correlations and describe them with the best way we can with mathematics. So we get an understanding of these different correlations between many observations we do. But the absolute reality behind this is not accessible, I believe, with the scientific method.
Thank you, sir. Thank you. And we have next question on screen, please. It is by Ritvik. Sir, can you give examples where we observe blue shifts in observational astronomy? Though redshift is quite common.
Yes, there are actually, when we look at galaxies that are not too far, their proper motion is actually large enough, and some of them are moving towards us, and there's a blue shift. I think there are over 1,000 galaxies that show a blue shift. So this shows that the Doppler effect from motion of the galaxies is also valid, of course. There is real motion of individual galaxies. But as we get far away, then the electron redshift becomes dominant, and this blue shift is not visible anymore because it's been compensated by the huge redshift at large distances.
Thank you, sir. It is very much interesting to know. Can we have next question, please? It is again by Dr. Bharat Pandey from Uttarakhand, India. Sir, does the Kapitsa-Dirac effect extend Einstein's relativity into the quantum domain by making photon properties interaction dependent?
No, the Kapitsa-Dirac effect is at very low energies for like normal light or so on. You could say 2 or 3 electron volts, let's say, or less. It's such at a low energy that in terms of dynamics, the classical physics is adequate enough. And so Einstein's relativity does not really enter into this effect. It's a quantum effect, essentially, with stimulated emission. But general relativity does not really enter because the energies are too small for these photon interactions.
Okay. I hope that answered the question. Yes, can we have next question, sir? Yes, this question is by Kumar Ravi from Swami Vivekananda University, West Bengal, India. In one of your slides, you showed a plot depicting angular size versus redshift. The redshift range extended to about z greater than or equals to 10. Could you clarify if that is observationally supported? I was under the impression that current observational data reach up to around z approximate to 8.2 from GRBs. Is the higher redshift data based on 2022 paper you cited?
That's right. Yeah, gamma ray bursts, I think, reach a redshift of about 8.2, although the redshift of those is much more difficult to determine. But the data I showed is up to redshift 14 and even further. So the most distant galaxy that has been confirmed with a spectroscopic redshift, that is, we see the actual spectral lines, is the photo I showed at redshift 14, that equals 14. And there are many more galaxies that have been observed by the Webb telescope at redshifts up to about 20, actually. But this is only from photometric measurements. So you look at the color of the galaxy and you sort of guess very inaccurately what its redshift is. So the data points that I showed on that graph are actually from the paper. They are actual measurements, and some are certain to redshift 14. And those that are not spectroscopically confirmed, still we have a large number of them. And so statistically, we can see from the color of the galaxies that these are galaxies that are extremely far away, and obey the statistics that follows the line predicted by in a static cosmology.
Yeah, thank you, sir. Thank you. So next question is from Professor Tejinder Singh. He is from Tata Institute of Fundamental Research, India. So are there observations which static cosmology explains better than expanding cosmology, or vice versa? Is static cosmology falsifiable?
Yes. So I think the two graphs showing the distance and the surface brightness, so the Tolman test, I think those explain better than expanding cosmology. There are still a lot of observations that are interpreted as an expanding cosmology that match data extremely well. And I cannot explain them yet because I haven't developed a theory, or nobody has developed the tools to analyze this and understand what's happening in terms of cosmology. And so when we develop this tool, that is, we derive the consequences of a static cosmology, we'll see what the results are. And of course, if they disagree, that would be a way to falsify the static cosmology. So a lot of more work is needed still.
Definitely, sir. Yeah, thank you. Last question for this talk. Can we have it on screen, please? Yes, this is by Dr. Ravi Sharma. He is from Nuclear and Particles and NASA Apollo awardee. He is from California. So his question is, in addition to E-photon interaction, what are relative strengths of other interactions such as EW and strong interactions?
At this point, I've looked at interactions with visible light or infrared or microwave light, and so these are all below even the rest mass of the electron, 500 keV, and so all these effects are very classical, let's say. And so now we know, of course, we detect very high energy photons in space, and that are way above the mass of the electron, the rest mass of the electron. And possibly then interactions such through the electroweak interaction, for example, they possibly would have some effect, but that's actually not my specialty. And so, if you're a specialist in high energy physics, of course, this effect, some effect may be equivalent to the Kapitsa direct effect, but with higher energy interactions, I think would be worth looking into, because there are a lot of things that are unexplained actually in terms of high energy radiation that's coming to us in space. There was this gamma ray. I forget what the energy was, but its momentum was the equivalent of the momentum of a tennis ball, I think, that was detected. This is certainly not what I'm calculating. This is way beyond what the equations I have can understand. So this is, yeah, really the domain of high energy physics. And but I don't have any knowledge so far or idea actually what would happen. But this is certainly a possibility, and it's worth studying, I believe.
Thank you, sir. Thank you. And yes, there is a lot more to explore, and we are still learning. Yes, thank you for addressing these questions with such wonderful insights. So, on behalf of
yes, thank you very much.
Thank you, sir.
Thank you very much. It's a pleasure.
And all the audience, I would like to once again express our sincere gratitude to you for sharing your insightful talk, which has opened up many questions among us. Hope our researchers who have joined will take a serious note of that and try to explore those questions and enhance their knowledgeability. And we would like to see you more often and know more when our time permits, sir. Thank you. Thank you once again.
Thank you very much. It'd be a pleasure to talk with you again.
Thank you, sir. Thank you.